Welcome everyone. Myself, Professor Himanshu Thaplial. Today I will give my talk on quantum carry look adder for NISQ and quantum image processing. This work has been done with the collaboration of two of my students, Edgar Munoj Corias and Vlad Khalas. Introduction: quantum computing promises up to supervolume speed up for many tasks. These include Hamiltonian evolution, unit group computation, factoring, uh, linear system operation, and scientific computations. Quantum circuits for arithmetic functions are required to implement several of these algorithms. Moreover, recently, quantum arithmetic circuits adders, such as adders, are already being used as the benchmark circuit in the NISQ machines. So you can think in this case that quantum arithmetic is a prominent area that require attention. So there are error sources in the NISQ computing. So what does NISQ represent? The NISQ is defined as noisy intermediate scale uh, quantum computing. So now there are error sources such as the coherence errors and the operation errors. These coherence errors can be defined through the errors. You can say these energy relaxation errors, or it can be defined as a dephasing errors. Similarly, you can have this operation error resulting from the gate errors and the state preparation and measurement errors. So for example, the gate error occurs whenever you perform some operation on the gates. Similarly, the state preparation measurement errors occurs during the preparation of a state and while you measure the final outcome, right? So, so if you see that measurement is one of the most error-prone operation in the NISQ machine, so that is very important for we need to, and we will see that why this is important actually. So motivation for these carry look adders, the arithmetic circuit as we discussed already are needed to implement these quantum algorithms. NISQ quantum computers have known sources of computational failures. And since this now the NISQ computers are right now of let's say within less than 100 qubit, it might be possible that in the future it may go up to 1000 qubit, but still they are not sufficient that you can put some error correcting codes on them. So there are some challenges. The challenge is that the total gate cost should be capped to minimum, and moreover, the quantum circuits on the NISQ machines require the shallow depth circuit. So this quantum carry look adder is one type of addition which is satisfy this criteria because it is a logarithmic adder. It has a depth of log n. So in this work, what we are showing you a design of this quantum carry look adder, which has also the reduced gate cost, which can be implemented with a low qubit cost, and also the depth, as I told you, is already logarithmic. So that's why it could be a good type of adder design for the NISQ machines. So this is one example here as illustrated here. This is so the QCLAs can be defined into two types. One of them is a in-place quantum circuit. Another is out-of-place quantum circuit. So difference is that if you see whenever you perform an addition operation, this B input is being transformed to the sum, while in the out of place, one of the ancillary lines you can say has been transformed to the sum output. So that's why one of them is called out of place, another is called the in place. Now we look into the building blocks. The building blocks that we will talk about in this work are the logic and computation gate. This is being represented here, and this is has been proposed in this work. And this gate needs an ancillary lines, ancillary t, which is initialized to this state, right? So and the t gate count of this gate is 4. So how many t gates are being used? So that is the t count, and it is has represent 4 because you have also this t gate is also being used here, right? So that's why it is 4. So now another interesting thing we look further is that there is also one logic and uncomputation gate. So if you see, this gate performs an like a AND operation, A and B, and this gate performs uncomputation of that gate that we have shown in the previous slide. However, if you see in this gate, there is also a measurement operation involved, and again this gate has been proposed in this work. So now what we think in this case, however, if you see this gate doesn't have any t gate, so the t count is 0. So these gates are very useful when you look into the machine which are fault tolerant in nature, because many of these operations doesn't have any cost while you look into the fault tolerant domain. Now the interesting thing is that uh, we think, and actually it is all, we think that based on the motivation that has been said in the paper. So what we think is that if rather than you performing that operation, what if we take this gate here and we do the reverse of this gate? So if we do the reverse of this gate, we will come out to this gate, right? And we call this gate as the computational reversal method, in which you are just reversing this computation. And the beauty of this, if you do that, you're not performing any measurement operation. And as I discussed with you in the previous slide, that measurement operation is noisy, and so we want to avoid the measurement. Moreover, if you look into the things, there is also some time computation associated with measurement operations. So, and because of which some other types of errors can also be associated. So we want to avoid the measurement, so that's why we propose this type of block, and the motivation has come from this work. So we as I told you, we perform the computation reversal method. Now, so in our design, we are using three blocks. One of the block has been, as I told you, is this block which perform the logical and this block, as I told you, is the reversal block, propose and computation gate, which is performing the reverse of the top block, right? This perform is the reverse of this one. So here you see this state is the ancilla is the T gate state, and here you are again getting the state back. This is another gate that's called the Toffoli gate, and this is the implementation of this gate in terms of Clifford plus T gate representation. So now we have these three basic building blocks available. And now what we did is that we tried to design some sort of adders based on that. So two adders we have designed. One of first of them is the out of place QCLA, and it follows some steps. There are some, so it follows these 8 steps in this algorithm. And the underlying idea is that if you look into this one, this is the algorithms, and more details of these algorithms can be found here, because this algorithm is modified from some of these two works actually. So you place the logical and computation gate, and these are the places where we modify the algorithm. So finally, this is an illustrative example. If you do that, you will get these are some of the gates which we replaced by the new building block that we discussed. And so what you can see here, that you will have new types of carry lookup adder, which has already optimized cost in terms of quantum gates, and moreover there is no measurement operation that is being performed in between. So this is an illustrative example. If you perform some computation, you will see that this gate has the lower T count, and we are just using T count as for calculation. But if you see, the underlying idea is that this gate will have the overall total number of gate less than the existing approaches. Now, another thing that you can think in this case is the in-place QCLA, and this algorithm shows the 16 steps, and these places represent that where we have replaced or modified the algorithms by placing the building block that we have discussed. So if you do that, this algorithm has again 16 steps, and more details of these algorithms can be found here. So what you do, you came out with again this new types of in-place QCLA, where we have placed this gate, selectively identify where we can put these gates so that we can avoid the measurement, and also how can we reduce the total gate cost. So we use this one. So finally, we came out with this design, that is in-place QCLA with reduced, you can say, T count equation, and moreover, you can say from that what we can derive is that the total number of quantum gates used is also less, and it has no measurement operation involved in between the gates, right? That's what. So now you can use this gate, and you can use this gate to design the condition, use this carry look adder to design the conditional adder. And the idea is that if the control block is high, then you will perform the addition. Otherwise, if the control block is low, then P will be equal to B. So by using this block, you can perform some multiplication. This is the example of the quantum circuit for multiplication. You can see the more details on one of this paper. It's a three-step algorithm. So the two building blocks for the quantum circuit for multiplication involves an array of Toffoli gates and a control addition operation. And we discussed already, and this is the illustrative example of the Toffoli gate. So this is the bigger Toffoli gates, like the Toffoli gates of the large size that you can place. So here we illustrate this example with a 4-bit multiplication, and if you see here, this is consist of a array of a Toffoli gate and some control additions, and finally you see these are the two numbers we are multiplying, and we get our final product here, right? So as I told you that this control addition can be designed from QCLAs, so you can design a low depth multiplier, right, which is suitable for the NISQ machines. Similarly, this work that we discussed has application in quantum image processing, and quantum image processing is being explored recently, and the arithmetic circuits form a major building block for that. So this is an example of the bilinear interpolation. So the idea is that by using some adjacent pixel, you can get the estimate the value of the pixel. Suppose you want to scale down an image or a scale up an image. So this figure represent, suppose you're talking about the grayscale images. Suppose you want to change the color. So the new color will be represented by a set of equations like this. So what you can identify here, that this equation consists of sum of series of multiplication, subtractions, addition operation, and many of these operations we have discussed already in the previous slide. So as I told you, we can have this building block like this. This is the addition, this is the subtraction, this is the multiplication operation. And now from these operations, you can derive this complete scale down circuitry, right? This. So you can say that this QCLA we have discussed can have application in image processing also. So in conclusion, we have shown that how can you design a resource optimized design of QCLA for the NISQ machines. And we have also illustrated that how can you use this QCLA to form building blocks for quantum algorithm with an example of quantum image processing.